Dear colleagues, my name is Ivan Palonik. I'm a member of the Russian team, and I'm happy to represent our solution to problem number 14, jump and beam. So, according to task says that if we put metal ball inside of plastic capsule and put it in inclined plane, it would go down in a surprising way. So we should find the dimension of the fastest and the slowest toys. Sorry. Yeah. So there's the outline of my report. First, I will talk about the excellent stuff which we use with exclude human factor. Next, we'll talk about the qualitative explanation of the phenomenon and find the dimension of the fastest possible beam. Next, we'll go to quantitative model where we'll describe all the motion of the system by parts. And finally, we'll go to parametric investigation. So the MSC setup which we use in our system, it consists of plastic capsules with different lengths, and we put balls with the same density but different radius to vary the mass inside it. Also, we realize the beams with the system you may see on the frame, which consists of motor, touch sensor, and computer. So it looks like you may see it on the frame. So there are two main advantages of this using setup. Firstly, we exclude human factor. And secondly, we can control role of three-dimensional motion on the system. And in most part of our experiments, we release our beam in order to move it in 2 dimensions. So now we go to the qualitative block. And first, let's see. So we have some inclination plane with some inclination angle, which is small enough. And we put a capsule on this plane. What happens in this case? So with capsule, nothing happens because sum of torques and sum of forces is equal to 0, so it doesn't move. But if we put a ball on the same plane, it won't move because sum of torques is greater than 0, and so it moves down while rotating. Okay, now let's combine the system all together and put metal ball inside a plastic capsule. What happens in this case? So in critical moment, when the system is near to start rotation, both normal and friction force will cross the z-axis, which we see on the frame, and so the torques around this x is equal to 0. Because of it, there are only 2 torques which can rotate the beam. There is torque created by gravity force acting the ball and torque created by gravity force acting the capsule. So our system can rotate if torque created by ball is greater than torque created by capsule. And of course, it's obvious that each of these torques depend on geometry and the mass of the thing. So now we write the mathematical expression for both torques for capsule and for beam, and find such this expression which talks us if our phenomenon can or cannot be observed. But it is not so easy to use such equation because it depends on geometry and the mass of the ball in the capsule. And while changing the geometry, we also change the mass. So if we derive it into one, you may see on the frame. So we use densities and dimensionless size parameters, and then we see good comparison between our theory and experiment for area in which we can observe our phenomena. Next, we'll go to quantitative block, and from the video on the frame, we clearly see that we can put our phenomenon in 4 steps. First is beam rotation, when both ball and capsule rotate. Next, this toy hits the plane. After the ball moves on the capsule, and finally, capsule hits the ball hits the capsule, and it starts to rotate again. So, on which of these 4 steps can we have energy losses? So, surely we will have them on plane collision and capsule collision. So, if you want to get the fastest possible beam, we should minimize energy losses in the system. And the result of such optimization, you may see on the frame. It is a beam with the size of a ball. So, it goes down without some energy losses. And from this video, you may clearly see that it goes down much faster than the beam with different parameters. So now we're ready to go to quantitative block, and we'll describe all 4 parts of motion one by one. Firstly, we should think somehow if our beam moves down with slipping or without slipping. We assume that it goes down without slipping. In this case, per each turn, it goes one distance expression for which we see on the frame. And we check it experimentally. So yeah, it's correct. Our beam goes down without slipping. So we will use it in our model. Next thing we should stated our model, this is location of the ball in the capsule while the rotation. And we assume that ball, capsule, and plane always have one contact point. So let's explain why do we think so. Let's, for example, ball go a little bit to the right. In this case, additional torque will be created, which will fastly rotate the capsule and coming back to the position when, again, capsule, ball, and the plane will have one contact point. And using this model, we may find the expressions for angular velocities of both ball and capsule rotations. So the last thing to explain the ball rotation is to write torque equation. We decide to write it about z-axis. And on this frame, you may see a system of differential equation, which is solved numerically, and there may see comparison between theory and experiment. As you can see, our theory of beam rotation predicts the motion of the system pretty well. Next, we go to the plane collision description. So if you work with with most planes, capsule stops after collision, and so both angle and binary velocity of the capsule becomes equal to 0. Of course, with very elastic surfaces, it may not happen, and we can just talk about case of elastic surfaces in the discussion. And the last thing we need to do is talk about how a ball moves on the capsule when the capsule stops. So we again write torque equation and find that it goes down on the capsule with constant acceleration. So, and the last in our model, but not the least, is to describe the capsule collision. So capsule goes down, hit the capsule, write angular momentum of conservation, and find the new angular velocities of capsule and the ball. So now we have to solve this system and check it if it agrees with experiment. Then we see a scheme of our numerical simulation. So we simulate all 4 parts of motion with general expression you see on the frames, and we can get from this simulation position of being as function of time, and also time needed for beam to go down for the same distance. So then we see a result of comparison between theory and experiment in our model, and you may see that our model our model can predict the experiment pretty well. And also you may see a video of the simulation of our simulation in the frame. And in the last in our report, we'll talk about the parametric investigation. So we firstly change the length of the capsule, and see what happens in this case. While increasing the length of the capsule, we increase torque created by capsule, which is decelerating torque in our system. So we decrease angular acceleration of the beam, and we increase time needed for beam to go down, which we see in our theory, in experiment, and what predicts our theory. Next, see what qualitatively happen if we increase the radius of the ball. In this case, we increase the torque created by ball, which is accelerating torque in our system. So we increase angular acceleration of the beam, and we decrease time needed for beam to go down. The same which you see in experiment. And the last, we make this experimental plot where we write both length of the capsule and radius of the ball. And with color, you may see time needed for this beam to go down. So from this experimental data, you may clearly see that increasing the length of the capsule, we decrease time of going down, while increasing the radius, we decrease this time. And also we find the dimensions of the slowest beam. To get the slowest beam, we should minimize the radius firstly, and after it, maximize the length of the capsule. And so then the conclusions of my work. We built experimental setup excluding human factor and controlling human 3D motion of the phenomenon. We found the area with which we can observe our phenomena. Talked about the fastest beam. The fastest beam is beam with size of a ball. After it, we had a numerical simulation describing all 4 steps of the motion one by one, which predicts the experiment very well. And finally, we write length of the capsule and ball size, also with good agreement between theory and experiment, and got the dimensions of the slowest possible spins. So that's all. Thank you for your attention. Now I must answer some of your questions.
Hi, so now I would like to firstly thank the reporter. Okay, I would like to thank the reporter for having a very good, overall I think it was a very good solution of the problem, because you started from like the theoretical approaches, you mentioned the parameters, and what I really liked was that you you introduce general parameters such as the gamma and the ratios of the masses, which was, in my opinion, very good. And then afterwards, you proceeded to explain to us, in your opinion, the fastest beam, and you showed like the comparison between the fastest beam and a beam with a capsule. And in fact, you showed that the fastest beam is just a sphere. And afterwards, you did some experimental work where you varied the capsule's length, and that was good. And also, I like that you divided the motion into 4 different stages, if I'm correct. And finally, I saw that it confirmed your model. And you also showed us like different experiments where you get the slowest beam, and with your graph, that was amazing. Okay, so now I would like to talk about the positive and negative aspects, in my opinion, about the experimental work. What I really liked was that you created a release mechanism where you remove the human factor from the experiment, and so that really confirms that you can get 2-dimensional motion. And next, you also showed us the difference between the fastest and slowest beams, where you varied the parameters. And finally, it's the reason like why you introduced the critical parameters like gamma and beta. So that was good.
Excuse me, I think we're having bad connection, and that's why you cannot read the slides. So we'll try to work on that.
Okay.
Meanwhile, I'll just continue talking. I hope you can. I hope you can get it. So, as I was saying, for the experimental work, what you did was very good with the making the beams slide in only 2-dimensional motion. However, for some negative aspects, what I noticed is there was one slide where you measured the position of the ball, and so I was wondering, how did you track the position of the ball? And also for your theoretical part of the work, you divided the problem into multiple stages, and you explained the phenomenon also of why it would start to tumble. So that was good. And finally, I also have some questions for you. So just give us one moment. Okay, there was you explained the reason why you explained to us how the model works, and that was what I like. However, for the theoretical aspect, there were some things that I noticed you didn't discuss, which is the perturbations of system. So, for example, I'm not sure if you have noticed, sometimes the beam may leave the surface, so I wonder if you had considered that. And also, how did you ensure rolling without slipping? But I like that you checked that there was rolling without slipping by the tracking of the position and time thing. However, I have some questions that I think we can try to discuss later. So first of all, it's about rolling without slipping. Like, how do you make it not leave the surface, and how do you ensure that it doesn't slip? And also, the size of the ball is smaller than the capsule in most cases that I saw that you use. And with this, there could be oscillations and effects of some results of the ball being smaller than the capsule. Like, I think that some things, it might cause some perturbation in the system. So I think we can discuss a lot on that. And also, I would like to talk about like friction, air resistance, and the boundary layer in the capsule that the ball experiences. And we can talk about that later more. And also between the stages of the motion, if I'm not wrong, you consider conservation of angular momentum, but I think we can discuss more. And also, did you mention that the ball reaches a maximum velocity, and why do you think so? So yeah, that's the end of the.
So can you please
Thank you.
off your presentation, I'll share my screen and answer your questions. So while you're doing it, first I'll answer the question about the position of the ball. So we made it in a program tracker. So we made the video, and after it we took it by pictures, and at each picture we found the position of the capsule and the position of the ball, and get its coordinate. Next, we have a question about slipping or non-slipping motion. So yeah, I agree with sometimes our capsule can move with slipping, and we can even theoretically predict if this motion will with slipping or without slipping. So to do it right, the second Newton law, as we know, the acceleration of the capsule, and we may find that if this expression is correct, it goes with slipping. And as you can see, it can, if the angle of inclination is smaller than 31 degree, it will always go down without slipping with all our parameters, all our right parameters of the beams. So is it clear? Is this question clear?
I'm sorry, could you repeat the last part? I couldn't really hear you.
Okay, I'll try.
Yeah, can you repeat the last?
Yeah, so the last one. So we found the acceleration of the capsule from our model. Next, wrote the second Newton law and finds that in transfer condition from motion with slipping to motion without slipping. So this motion with slipping friction force will exactly equal to friction coefficient multiplied the normal reaction force. And combining this first equation together, we get the equation for maximal angle with which we have motion without slipping. So, and of course, it depends on geometry of our beams. And for all our beams, this angle was higher than 31 degree.
Okay, I thought it was actually a really good idea, but I was wondering, like, because there are two forms of rolling without slipping. Firstly, you had to make sure that within the capsule there is rolling without slipping, but also the capsule itself with the surface. And if you have found the condition in experimentally, how did you ensure that the surface was had enough friction? Like, did you use another surface, or was it
Yeah, we
coincident?
use we've made experiment with other surfaces. For example, on this float we get experiment with wood, paper, and tape, but with small inclination angle. So because of this inclination angle was small, we had motion without slipping, and because of it, we see that roll of the surface for small angles is so the surface doesn't play a role for small angles. But if we would have inclination angle higher, for example, about 45 degrees or even higher, in this case, surface will also play one of the most important roles. But with small angles, surface doesn't play a role for friction, but it play a role for elasticity.
I see. Yes, I am.
Because
I agree with you that the
it's about
friction
elasticity.
is fine here, and that there is rolling without slipping. Oh, okay. However, there's something else that I noticed. You see in your video here, for example. Well, there are a few things that seem to be perturbating the system a bit. Firstly, you see the capsule hits the floor, right, and it starts bouncing, and the ball is like, it starts rolling down the capsule, but the capsule is like moving up and down. And how do you think that affects the position traveled by the ball?
As I got your question, you're asking on the same motion of the ball as you can see it on the frame when balls jumps after collision and ball continue motion after it. Is it about it?
But do you think that the ball will still continue in the same position, such as like in the beginning you showed the first rolling phase where the ball rolled down, right? And then it was like a curve. But over here, do you think after the capsule hits the ground, is it still gonna have the same shape or different?
I think it very depends on elasticity of
What do you think?
the surface. I think it depends on elasticity of the system on the surface because from this video it can be clearly seen that if we increase the elasticity of the system, it won't be so. But as you could see from on the videos for the presentation, for example, this one, sorry.
Yeah.
For example, for this one, you may clearly see that in this case, capsule doesn't jump after collision, and the ball is at the same position as it was before the hit. So this elasticity of the surface is parameter for this question.
I see.
And at this point, we can invite team members to the discussion.
Not elastic.
Sorry, I didn't hear you.
So let's say the surface, you have chosen it to not be elastic because you don't want the perturbations, right? Then how does this affect the conservation of angular momentum between each roll down? Will angular momentum still be conserved, or what do you think about the energy of the capsule?
Yeah, okay, so I got the question. We talk about the angular momentum conservation only at the moment of hitting the capsule. So only this angular momentum is conserved only at this moment, only about moment of collision. So of course it changes. Of course, with the time of system motion, angular momentum changes. But because of the collision happens very fast, and all the forces cross that axis, because of it, we say that the angular momentum is conserved during this collision, but not for all time.
Okay, I agree with you.
Okay,
but,
again, any remark from team members? We can do now remarks
So
from team
let's move on
members.
to the next discussion. What do you think about the air resistance that the ball feels? Or also, if the ball is almost the same size as the capsule, how do you think it will? Do you think it will be affected by the air that's being squeezed through the sides of the ball? And like, what do you think are the conditions that in what conditions would it be non-negligible?
So firstly about air
Did you
resistance.
understand?
Yeah, I think I understand it. So firstly about the air resistance in our model, we neglect it because we assume that because we think that it's neglectable small. But if you can, but we can discuss it with you. Maybe try to get estimation value of this and find out if it is important.
Yeah.
But so if you think that it's really important,
Okay,
we can discuss it.
Yeah, I think. No,
So
actually, I
what do you
think
think
it's also
about it?
negligible. But one thing I was worrying about is if the ball is almost the same size as the capsule, then does it squeeze the air out, and does it cause some kind of turbulence?
Can you clarify how will this air go out of the capsule? Because if it's so can you clarify it to me what you mean?
Okay. For example, if the ball is very big and you put it in the capsule, like it's so big until it can't move. So that could be one possibility, right?
So is it do I make it? Do I get your idea clear that you have capsule with size of a ball and size of and ball is slightly smaller than the capsule?
Okay.
Yeah, is it your idea?
Yep. Yeah, that's okay.
So okay, in this case, yeah, we can. So.
Sorry, what?
I don't know, someone interrupted.
Okay. Let's move on.
Okay, so in this case, if it's...
I had a question about your...
Oh, okay, ask.
Don't you? Okay.
I had a question about your experimental setup. I wanted to know how you measure the position of the beam on the plane that it is rolling on.
So we take, so we had the plane and we have camera 2 meters from the plane, and we took video on this camera, and after it in a tracker program we so on each picture of this video we took the position of the ball, and after it we get how does it change with time. Did that answer your question? Did I answer your question?
Okay, thank you.
And
you're free now to ask questions.
How do you ensure that the movement is indeed a 2D movement as you had?
Yeah, so we say that
the chairman said something. Okay. So the question was, how did you ensure that the movement of the beam was two-dimensional, as you said in the beginning?
So yeah, okay. Let me clarify it to you. Sorry, so long opening. So we had our setup. It looked like this from overview, and we could clearly vary this angle. You may see it on the frame angle phi. And in most part of our experiments, it was equal to 0. But we had special investigation when we vary this angle. And because if it was 0, we can say that our bin moves in 2 dimensions. And also it was from the video.
Okay, thank you. At that point, we interrupt the discussion. And now the reporter, you have your time.
Yeah.
You have your time for concluding remark.
Yeah, so I'd like to thank the opponent for his work, because he helped me to explain some not clear ways of my problem. For example, tracking of the video, methodic of video tracking. Also, we talk about important parameters, important questions in this problem, such as motion with sleeping or without sleeping, and also found out that with some specific condition, a friction also can be important. But it was a good point to add this specific case in my report. And we also talk about the role. We also started talking about the role of 3D motion. So, in my opinion, this discussion was pretty productive. And thank the opponent once more.
Okay, so I'll start. Yeah, I enjoyed very much the presentation and the discussion, but there is some point that is missing, and so I'm going to ask the same question for both report and opponent. It's a very old toy. I used to play with it when I was a kid here in Brazil. And something that surprises me is that there must be a mechanism that keeps the energy constant. That's why the ball the beam doesn't accelerate during its trajectory. And I didn't see it in the presentation and in the opposition considerations about which mechanism keeps the energy constant while it's going down. So I would like to ask you if you have any ideas of which mechanism would, which loss mechanism keeps the energy of the beam constant over the kinetic energy constant over the trajectory.
Yeah, okay, so I can answer the question. Firstly, the energy of the beam, kinetic energy of the beam increase as it goes down, because it's energy transfer from potential energy to kinetic one. So kinetic energy should increase, but since some moment it doesn't increase because of we have energy losses in the system for non-elastic collision between ball and the capsule, and also between capsule and the plane, which you may, these two collisions. Just a second, please. These two one, when plane collision and capsule collision on this frame. So these are ways of losses of kinetic energy, and kinetic energy increased by the gravity one decreasing. And since the moment losses and increasing becomes equal, and so because of it, total energy for one turn is conserved.
For my answer, what I think is that, so initially in the first row, when the ball rolls down, it gains some kinetic, it did gain in kinetic energy. But the thing is, between the point where the capsule hits the floor, so when the capsule hits the floor and the ball rolls down, and the whole thing starts to turn around, there's actually perfect conservation of angular momentum. However, when the capsule then falls down and hits the ground, right, the ground actually absorbs the energy from the capsule. And so the correct way to do this would be to consider only the continuity of the velocity of the ball at this point. And so each time you keep rolling down and you hit the floor, you're actually losing the energy of the capsule. And this is what will, so as long as each time you roll down and the energy that you gain is the same that the energy that you lose that you get from hitting on the floor, then it will start to become in terminal velocity. And actually, may I talk about my problem? No? Yeah, okay. Yeah, so actually that's what I think will cause the kinetic energy to stay constant after a while.
Okay, thank you. Sonia, let's move to your question if you have any. We don't hear you.
Sorry, I was muted. Okay, question to the reporter and then one to the opponent. So to the reporter, imagine you don't have light. So you have to do this experience. You have your setup at a certain point, everything is shut down. And so the only thing you have is a small light at the point of your capsule. So basically you can only follow the trajectory of your beam going down, do you think you could still answer any question of the problem? You can still get any information only looking.
Sorry, can you please rephrase your question? I didn't get it.
Imagine you are your beam, okay?
Yeah.
And there is a small light in one side, one edge of your beam, okay? For example, I see the picture you have now shared, no? The first, the one you have on the left, where there is the small ball. This is a small light, okay? And then everything is dark, and so you just see this light going down, so you can see in the dark the trajectory. Do you think you can still extract any information only having the information of the trajectory, and then of course you can study offline this trajectory and the timing? Maybe. I don't know.
I think
Your
yes,
feeling.
I think yes, we can do it, but I think that the accuracy of this method will
yes, of course, the
will be much less.
will be not the same.
Yeah, so I think it's still possible, but with low accuracy.
Okay, one question to the opponent. Talking about the small ball inside the bin, do you think what could be the effect if I put some oil around the small ball? Do you think this could affect the results we got? Simply putting some lubricant around the ball.
First of all, if we put oil around the ball, then within the capsule, there won't be rolling without slipping. So the ball will just go down, and I think it will exert, because it won't exert friction onto the capsule, it might have some trouble trying to turn the capsule, in fact, because in
Not
order for
outside, inside, I'm saying, inside.
it's inside.
Yeah.
Yeah, so there will be no more friction between the ball and the capsule, right?
Mm-hmm. No, the ball has some oil, and then everything is closed in the capsule.
Oh, so the capsule is filled with oil, is it?
Yeah, the capsule is normal. It's only that you put some oil around the small ball inside. So you change, if you want, the friction between the ball and the inner surface of the capsule. Do you think this could be a negligible effect? There should be an effect or not? What is your feeling? Just a feeling.
Well, first of all, there won't be any more friction between the ball and the inner side of the capsule. So that means if it starts to roll down and it starts to lift up the capsule, I think it may not lift the capsule as much as if there were a lot of friction between the ball and the inner side of the capsule.